I think finding phosphine on Venus is one of the big reasons why you pivoted into working on the Venus Morningstar mission. So what are the Venus Morningstar missions? Why is the finding of phosphine so exciting? And why do you think that might be a marker of the presence of life there?
Right. Well, phosphine on Earth, again, let's just allow ourselves to be terracentric for a moment.
Okay.
Phosphine on Earth, it is only produced by life. I mean, well, maybe there's one or two exceptions, but it produces like negligible, like almost nothing. So phosphine on Earth, it is made by us humans as insecticides and pesticides. Phosphine appears to be made by bacteria in oxygen-free environments like wetlands and other places. And so it has unique spectral features. It can kind of reasonably accumulate in atmospheres. It is still pretty reactive. Yeah, so phosphine, my team, we were working through we were searching for the ideal biosignature gas. And phosphine popped out right away, and we wrote a bunch of papers on it. And we discovered that someone else was working on phosphine as a sign of life, unrelated to us. And it's such an obscure gas. I mean, most people have never heard of phosphine. It's a phosphorus atom attached to 3 hydrogen atoms. And in fact, we have phosphorus on Earth. It's part of our DNA, but it's usually attached to oxygen because we have so many oxygen atoms here called phosphates. So someone connected our two teams. And the other person was Professor Jane Greaves, purposely searching for signs of life on Venus by way of phosphine gas, because she's a radio astronomer and phosphine has a radio signature. So she invited us to join her team. That was pretty exciting. Let's cut a long story short and say in the fall of 2020, we reported the detection of tiny amounts of parts per billion by volume of phosphine in the Venus atmosphere. And the reason I'm looking like this is it was not a hit. It was a extremely controversial discovery. And to this day, it is highly controversial. And so there's 3 reasons for that. And these are the same questions we would have to ask about any future exoplanet discovery. Is the signal real? I mean, these are tiny signals we're looking for, right? Like think about trace gases or noisy data. And some astronomers have not recovered the signal in the data. The data is all public. Some astronomers have recovered the signal, and that leads to the second question. If the signal is real, like we found a signal, did we attribute it to the right gas? Is it phosphine or could it be another gas? And then one other contender is sulfur dioxide, which we know exists on Venus. Now let's assume those first 2 are correct. The signal is real. It's attributed phosphine is the right gas. Let's say we believe those 2 things. Then we have to ask, is phosphine made by a non-life process? And our team wrote 100 pages explaining why it can't be made by a non-life process. But, I don't know. I don't want to say quantity is not quality, but there could be something we overlooked, and we certainly leave room for that possibility. There could be other chemistry we don't know about yet, but it would be pretty hard. So those are the reasons why it's remained incredibly controversial. But for me personally, this was like a career crisis. Right, think about this for a moment. Spent a lot of years trying to find the ideal biosignature gas.
It's right next door.
It's right next door, and no one believes it for a lot of reasons.
Yeah.
So let's think about that for a moment. Now think about a distant exoplanet. Noisy data. Is the signal real? Is it attributed to the right gas? Is it made by something other than life on what's essentially just a dot in the sky? Like, how am I going to continue to invest whatever 15, 20 years I've got left as a researcher when people may never believe it? It's like you don't know whether to laugh or cry because it's so absurd.
I don't know why this ranks on the giggle factor.
I don't know if it does, but it's pretty depressing, I'll tell you that. So in order to figure out what I was going to do with that thought, I took some time away from exoplanets and decided to leverage this phosphine opportunity into asking the question, can we go to Venus? Can we send space missions to Venus and search for signs of life or life itself directly in the atmosphere? And that's how the Morningstar missions to Venus, an international consortium that I started and run, came to be. Now, wait, one more thing, though. We used to call ourselves Venus Life Finder missions. But did you know there was so much pushback? Like, which one do you like better? Venus Life Finder missions or Morningstar missions to Venus?
Why is there so much pushback in the community towards the presence of life? Another professor in the Cambridge area, Avi Loeb as well, has spoken extensively about Oumuamua as well.
Right.
And it feels like the number one, the gut reaction to all of these findings has always been very negative.
Yeah, very
in
negative.
general, why is the community against finding life?
So we've been actually, in my work, believe it or not, we've been convincing people to believe, actually. Not that there is life, but that there could be, because we're doing repeatable experiments. Now for Avi, for Oumuamua, that thing's gone. They can't do any more experiments on it, but they can hope to find other cases like it, right? So I do have an advantage in this area. So why people don't believe, I mean, you only need to Google sulfuric acid and sugar, because our DNA has a sugar molecule in it. And sulfuric acid and sugar, it is not pretty. It's like, whoosh, it is insane. You have to look that up later. And so there's reasons why our life, like on Venus, the surface is too hot for life. But just like on Earth, when you go in an airplane or you go higher and higher on a mountain, it gets colder and colder. So on Venus, we're not talking about life at the surface. We're talking about life in the clouds of Venus. Well, the clouds of Venus are not made of water. They're made of concentrated sulfuric acid. So, I can tell by your expression, like almost how old you are, because there's a generation that knows exactly what sulfuric acid is. And that's the older generation. Because remember how it seems like there were no rules in the old days, right?
Right.
There were no car seats, there were no seat belts, there were no limits.
Yeah.
And when I talk to older people, they're like, yeah, I use that in the basement for like my chemistry set. It's like, what? Like you can't buy that stuff. I mean, it's so dangerous, sulfuric acid, right? So why do people not believe there's life in the Venus atmosphere? Because concentrated sulfuric acid is a nasty, deadly, toxic chemical to all of our life. We use it to clean electronics. Like here at MIT, one of my students found some other student who said, hey, you should go to MIT Nano Lab. They use sulfuric acid. Maybe they have some lab space you could get. I have my own lab now, but when I was trying to get some labs, and you know what? They have these giant vats of sulfuric acid to clean things, to kill life. So that, was like a 30-second meeting because we got there and realized there's no possible way it's relevant. But we still got a tour of the MIT Nano. So that's why people can't believe it, because it's so ludicrous. But what we've been doing is tied to the missions and tried to motivating the missions. I have a chemistry lab here at MIT, and we put molecules in concentrated sulfuric acid. So our DNA doesn't survive. But here's the thing, part of our DNA does survive. The latter part of when you think about the double helix, there's a ladder, and we have adenine, guanine, cytosine, like ACGT, those survive. They get protonated, they get, a little bit altered by the acid, but the ring is there, the whole structure it lasts for more than a year. We put our amino acids. Most people know what amino acids are because they make up protein. Some people who are into bodybuilding, how you have to eat a lot of protein to gain muscle? Some people buy amino acids and eat them. So people know what they are. So we put our amino acids, remember the component of protein, in concentrated sulfuric acid. And guess what? Stable. With one exception, stable. They're half are chemically modified, but they are stable. We've been experimenting with small proteins and with fatty acids. And sure, there's a lot of chemicals that are not stable, but there's this growing list. It's the tip of the iceberg of chemicals that are stable. So now when I talk about all this chemistry, I go to a different university or I meet some other scientists. They can't deny this. These are repeatable experiments. But then we have to go to the next level. Now we need an energy storage molecule because you need it. We eat food, but we store energy and then we release energy. So, it's complicated, but just let's say these laboratory experiments are to motivate the missions. Because if I can come back to you and say, hey, our DNA is unstable, but we have made a DNA-like molecule, swapping out unstable parts of our DNA for stable parts. If I can show you a kind of similar thing to DNA, an informational storage molecule, I hope you'll be sold.